Okay, welcome back. I have the input from Greg that he liked to see the more of this data from the MagLab. So I decided that I chose this topic that most of the data, in fact, coming from the MagLab, and yet kind of getting into splits of the this interesting the correlation of the quasi-particles in this two-dimensional system. So particular one that I want to talk about is this magneto-exciton condensations in quantum graphene double layer system. And we'll touch upon some kind of things in general context. All right, so let me first introduce the collaborators on this particular topics. And most of this experiment was done in the Xiaomeng Liu and in the help of the Zhou Hao. And then we have the quite a collaboration as well as competition, depends on the certain part of the talk, with the Columbia groups, Leo Lee and the Corey Dean, the Jim Hahn. And then again, that already I mentioned a lot of progress in this two-dimensional material field is using the really high quality of the boron nitride, which comes from the Japan. And in terms of the theory, that we got great help from the Bertel-Perrin. So talk will just go over probably about 3 papers that 2 published here and 1 is in preparations, but also there are a few other related parts that I'm going to mention. Right. Okay. So let me start with the kind of general background. I think as a physicist, that 2 most exciting the condensed matter phenomena is, I would say, the superconductivity and superfluid, and both of them actually demonstrated macroscopic states of the certain quantum state in the rather robust way, right? One thing common about this robust quantum effect of superfluid and the superconductivity is basically the underlying the quasi-particle, underlying the system is basically described by the boson rather than fermions, right? Of course, the superconductivity in simple BCS type of the idea that there is a condensation of Cooper pair can explain this superconductivity. Of course, this Cooper pair, a pair of the 2 electrons as a composite particle, we can just say it is boson. Superfluid helium, for example, it's helium-4 is responsible for the Bose-Einstein condensations, where that the helium-4 is, of course, a boson. As a composite boson, in a sense, it consists of a lot of particles there. So often that the composite boson is quite important to describe the robustly this macroscopic quantum state that we've been seeing in the nature, right? There are a few different examples of the forming the bosons, though, and also hence the Bose-Einstein condensation. One of the examples that we are looking for is like the exciton, for example, right? In semiconductor, typically when you shine the light, you excite the electrons in the field band to the empty band, and then leaving the hole behind, an electron hole by Coulomb interaction, they just form the bound states. And for a moment, although this is excited state, and therefore is a kind of rather transient state, for a moment somehow, let's say, assume that exciton is live forever. If I have such a long-lived excitons, and we can just ask what is the quantum nature of this exciton, because this is electron on missing electron, which we call the hole. Both of them are fermion, because then the exciton, as a kind of composite particle, should be bosonic states. Therefore, it's kind of naturally think about if the exciton is really long-lived, maybe we can just draw this composite bosons, the phase space. And of course, in the down in the low temperature, boson will condense into the Bose-Einstein condensations and make some sort of the exciton condensation. It turns out, depends on the density of the exciton. However, this condensation state can undergo maybe different states. For example, if the exciton distance is far away compared with the size of exciton, this you just really trick like this real space independent bosons, and they will condense down to Bose-Einstein condensations, and we can get the exciton condensation states. If, however, the density is high and exciton is very close to each other, in some sense, you cannot just kind of identify which one is which electron belong to the which excitons, which hole is belong to another exciton. So in a sense, in the extreme limits, it's better actually described by the strongly interacting electron hole as a soup. And they're actually well-defined the descriptions of, again, that the BCS type of superconducting condensations can be described in that way. It turns out between this BEC versus BCS description, There's no sharp distinctions, and there's crossovers can happen. And this type of the crossover, in fact, has been seen in atomic AMO physics, just using this two diatom the fermions. Each fermions form the diatom molecules case, right? In Exton's case, as you're just kind of going out of the condensation, you will just get into the normal state. Either it can become Exton gas or the electron hole Fermi liquid, depends on the gain density. And supposedly between this Exton gas to electron hole Fermi liquid plasma state, there's another transitions or crossover, what you call the mode transitions, can happen, right? So basically that is a phase diagram that expected, and that's solved for. It has been really difficult to realize this type of Exton condensation, Exton phase diagram. Part of the reason is the assumption I made, if the Exton is live very long, is very difficult to obtain, unless very clean materials, right?
Just to make sure,
yeah.
By BCS here, you don't mean a superconductor, right? It's a pairing between electron and hole.
Well, so again, that can be condensated into superconducting state in principle, right?
You have insulated there.
Well, okay, so now Exton state is an interesting state because it's insulating in a sense because Exton is still charge neutral, right?
Yeah.
So in a sense, it cannot just carry the supercurrents.
Exactly.
Yeah. In that regard, it is different. Even if it is BCS coherent states, it's not the superconductors per se. Yeah. Right. And of course, there has been some way that to realize that this type of condensation in the field, and community that work on this field kind of several decades really rely on that how to increase Exton's lifetime to just realize this kind of thermodynamic phase spaces. One good example is just using the semiconductor heterostructures, where that you have the two quantum wire is separated by just the tunneling barrier in between. In this quantum well, that you excited the Extons in one of the well, and if you bias this quantum well and separate the electron holes, they're leaving into the opposite quantum well, at least they still form the Exton by the Coulomb interaction as long as this two quantum well distance is small. However, now the tunneling between this the electron the hole to recombine the Extons, the recombination of Exton is rather difficult, and then Exton can tend to kind of live long. In such a system, there has been some report that indeed Bose-Einstein condensation like the state, such as, for example, the spontaneous coherent states appears in those kind of soup of these Extons that live in the different layer, often called the interlayer Extonic system. Although this has been seen, well, that it is still not perfect. Part of the reason is, yes, lifetime is long, but not infinite, right? Typically the lifetime, I just didn't have, lifetime of those kind of interlayer Exton is still about several microseconds, and binding energy of those Exton is relatively small because of strong screening of the system. Therefore, this type of effect is rather subtle and difficult kind of pursue. And of course, that when this 2D material arises, this type of this approach is resurfaced back. Part of the reason is, well, in the 2D materials, there are a bunch of the semiconductors available. Once you they shine the lights, there's Exton formations. And moreover, this Exton is very strongly binded because all the Coulomb interaction, the Coulomb interaction between the electron holes, leaving outside the materials, there is no screening. Therefore, the binding energy of this Exton can even just attain to be several hundred millielectric volt, which means it becomes quite robust, right? And also, there has been some way that increase the lifetime of this type of the Extons in 2D materials. Just following through very similar the idea. Basically, you just form these quantum wire structures. In this particular case, just choose two different semiconductor in the 2D TMDC, transition metal dicharge coordinate, for example, moly diselenide, tungsten diselenide, N-type and P-type, and put them together. You form this type 2 junctions. When you shine the lights, you can just create the intralayer Extons, but then also it can turn into the interlayer Extons. And in fact, like the combination of the device fabrication I just mentioned, you can just kind of form these devices with all the gate and contacts and shine the lights, so you can get this interlayer and intralayer Extons in a very sharp sense, right? Once you form this interlayer Extons in those kind of heterostructures, it turns out that they tend to live quite long, and the lifetime becomes something like easily about microseconds and 10 microseconds and the levels. And shine more of the lasers in there, you can create this more of the extons, and then their binding their energies, the photoluminescent energy increases. And part of the reason is you just stuck in the many extons in the small space. Their dipolar interactions start to push their energies up, and this shift of the energy allows us to estimate what is extons that we can create in this way, right? It turns out we can create about 10 to the 11 extons per square centimeter before we heat it up, just to simply kind of form these heterostructures. Now, this is rather significant numbers. However, if you just plug in these numbers to get this, what is the expected extern condensation temperature? It turns out that's about kind of a fraction of the Kelvins, right? So still, we have quite a long way to go to create those kind of extons and extern condensations. Good news here is, in principle, one can use the p-n junctions to just kind of form the traps and then just inject extra electrons in a hole by the electrical means. There's a room that you can actually increase this number even further. Therefore, the extern condensation can be potentially realized in this type of this real extern system. But nevertheless, all the real extern is transient particle, which means that this condensation, even if it's realized, it is quasi-condensation rather than really thermodynamic states. So that's kind of something that we know. However, this already gives us enough motivations. There is a way that we can realize extern condensation in a very analogous way in different systems. And that different system is, again, two-dimensional electron system formed quantum well, as we just kind of discussed in previous things, but without shining the light, but populate this quantum well with electrons or holes in both, right, and apply the magnetic field. And that's kind of has been known as a so-called quantum Hall bilayer system. And this quantum Hall bilayer system has been studied many decades now, I think starting from just late 80s, and then series of the seminal work done by the Jim Eisensteins and others around the time, and make this kind of things kind of quite exciting platform. One can realize exciton, more precisely magnetic exciton condensation. Let me just briefly explain how that works in the conceptual level. So imagine that I have the two layers of the electronic system, apply the magnetic field. And applying the magnetic field, we know that there's a Landau level forms in quantum conditions. Once you fill up the Landau levels, then you get this quantum states. But imagine that you just filled up the Landau level only partially. Either you just kind of apply the incommensurate magnetic field, or just kind of using the gate to control the density. But anyway, both of the Landau level is partially filled. Now, partially filled Landau level is a kind of boring system, unless you just have the very strong electron interactions. In partially filled Landau level, in semi-classical way, it's kind of bad matter. So nothing special things happen. There's a lot of dissipations can happen, right? However, let's imagine that these two Landau level, two layers are close by, and then they are filled up in such a way, each of them are partially filled, but together they can be kind of completely full. So it is complementary field Landau levels, right? And when you just kind of think about these two layers are very close by, there's interesting the interactions can happen. Interaction is simply just kind of Coulomb interactions. So when there's an electron is on the top, the bottom layer electron will just try to kind of avoid this top electron, so create the holes in the bottom layer, right? So it's like the kind of Hartree type of the interactions. And then you can see that if this is partially filled, and there's also partially filled or completely filled, whenever there's an electron, there's a holes on the bottom layer, right? Another way to say that is, if I just kind of look at this two layer when it's close by and just look from the top, if we just project it, as if that if I just project two layers together as a one layer, they form like the one full Landau level. Therefore, that you expect actually there might be quantum Hall effect as a one single entity is there, right? Although microscopically closely look at it, and electrons and holes that's kind of avoiding each other, such that I can just always put this dipole moments that either from electron to the hole in the side, and then staggering form of the dipole moments. However, as a projection, they fool the full quantum Hall effect with this nice edge state, which can carry the current dissipationlessly, right? So this is kind of conceptual level of the descriptions. The mathematical expression you can just make of course, all this different configuration is allowed, can be neatly kind of summarized into this ground state wave functions there, where that the electrons and holes are linearly coupled together and form this kind of the ground state wave functions, nicely describe all these kind of possible states that I just mentioned. Once you just put up there, this state is very close to, in fact, that when we just kind of form the excitons and condensation of the excitons that can be written in kind of similar forms, right? So this type of the idea has been presented that when quantum or bilayer system has seen. And experimentally, actually, this has been shown. Here is a kind of one of the seminar experiments was done in the Einstein group after all this technical difficulty they overcome. So as you see here, that when you just have this is each of the layer is the full field, and then down and then even go to the higher magnetic field, you start to empty out this the first Landau level for each of the layer. Supposedly nothing happened until that you hit this sum of the fractional quantum Hall states. But what is interesting thing is exactly when both of the layers is about the half field, there is a re-entrant of the quantum Hall state appears, exactly kind of described by this type of the states I just mentioned, right? So we know that in the quantum Hall bilayer, then indeed this type of the re-entrant state is happening. But more exciting part is not only just kind of quantum Hall state. Now in this bilayer system, if you have the contact in both of the layer, you can do the following interesting drag experiments, right? You send the current in one of the layer and measure the voltage in another layer. It can be longitudinal transverse, so you can measure drag resistance or drag hole resistance and see what happens. And this experiment shows that drag hole resistance is quantized, and the drag resistance actually goes to 0, right? So it's an interesting system. In fact, those kind of the quantized drag hole resistance, which is significant, can be explained in kind of following way. So remember that once that this magnetic exciton is condensated, you can view that it is a magnetic exciton condensation in the bulk. Therefore, there is a superfluid kind of flow can happen without dissipation. Now, this is a superfluid, but it's chargeless because it's electron holes that kind of moving together in the same directions. But in terms of the current of each of the layer, there basically this exciton flow can be viewed as a counterflow of the current can happen without dissipation, right? While that, as the quantum Hall states, there is an edge state also can carry the current. So any current you're sending in the system, you can decompose two components of the dissipationless current. One is the quantum Hall edge state, and the other one is this superfluid state, which current is flowing counterflow geometry. And together with this one, if you just solve it, you can show that indeed the consequence actually appears as quantization of quantum Hall drag into the quantum states, right? Perhaps probably the better way to describe that those kind of the exciton condensation state is directly prove this the bulk exciton currents. And this is possible, especially if you have the contact in both of the layer, basically sending the current to one of the directions and returning another directions. Since the current is flowing in the opposite direction, this will just move the excitons dissipation-lessly in the one of the direction. Therefore, this counterflow geometry, you expect to see that 0 counterflow resistance in this particular case. This is kind of exciting. Part of the reason is, without this, if I just measure current here and current here separately with the voltages, basically each of the layer is resistive. However, once you just kind of connect this two layer and return the current in opposite direction, somehow this two bad metal turn into the kind of superconductor in counterflow geometry. And this experiment was also done. A series of the experiments done in the Princeton's and the Max Planck Institute and the Caltech. They undoubtedly show that indeed, once you just kind of connect this the quantum Hall bilayer in counterflow geometry, you start to see that there's 0 resistance in the counterflow geometry. Okay, so with this, basically, obvious thing that we can do is just repeat this experiment with graphene, right?
Sorry, for that.
Yes.
In your previous slide.
Yeah.
Before.
Yeah.
In your ground state wave function, why are you linearly combining electrons instead of electron and hole?
Let's see. Yes, so this is basically, okay, so good point. Right, in this geometry, basically, I just add up the electron there, electron up there, right? So it's electron to electron combinations. the way that I can just kind of interpret that this is hole is, instead of this is the electron, I will look at this the empty side is which is a hole, right? So the way I can just do that, instead of them just applying this one, I just kind of reconfigure this one into the whole if I just define my vacuum states with kind of particle conjugated, this can be rewritten in terms of electron hole, and this can exact the analogy works in that way. Yes. Okay. So if we just kind of do this experimental graphene, of course, I showed you this type of the device geometry before, 2 graphene layers separated by boron nitride. Especially we use a relatively thick boron nitride suppressor tunneling between the top and bottom layers, and that's kind of important aspect of this experiments, and the top and bottom gates and all these contexts and do the experiments, right? What is not shown? Oh, well, we get the kind of very similar analogous result than in the previous case, except that in graphene that we have a lot of these more controllability, especially we can control the density from 0 electron hole and to the quite high density. Compared with this gallium arsenide heterostructure, this allows us that we can just create this half-field Landau level or full Landau level at high magnetic field such that we can make the energy scales much larger. And that's kind of one important part. So we start to see that this all the effect that is seeing that in gallium arsenide, such as quantized drag hole, zero counter resistance, and then obviously not only just one half-field Landau level of the electron Landau level, we start to see that between the different Landau level also you can make this magnetic condensation can happen, right? So that's kind of exciting part. But most exciting part is, in some sense, we can just realize this condensation state is a relatively high temperature. And the reason that we can just kind of make this high temperature condensation is part of the reason, first of all, that we can make this electron hole layer, the 2 quantum layer separation small, such that we can make this binding energy strong, that first of all. And second, we can just kind of make this half-field Landau level can happen in larger density. Therefore, we need a large magnetic field. And large magnetic field is helpful because the Landau gap becomes larger in the large magnetic field. And that allows us to make the phenomena is rather robust, such that we start to get this even signature of condensations around even just kind of several Kelvin, kind of 4 or 5 Kelvin. Already we start to see that this signature of condensation, while that in gallium arsenide, typically this has been seen below 100 millikelvin, right? Okay, so why this higher temperature is important? Because that allows us now, we can map out the phase diagrams a little bit more carefully. So what I'm going to show you next plot is basically we use experimentally chosen order parameter, I would say, such that we just kind of connect the sample in the counterflow current geometries and sending the current in one directions and return on other directions. And we measure this counterflow resistance as a function of both magnetic field and temperature, right? While that we just control our gate such that we always stay in the total filling fraction 1, basically 2 half-field Landau level, staying there and just measure how the counterflow resistance got changes. Remember that signature of the condensation is counterflow resistance goes to 0, right? Yes?
Can you explain this figure a little bit, how the leads are connected?
Yeah. So basically, in principle, that we can measure the schematics, but okay. With the black arrow is basically the direction of the we can flow the current, right? And this lead is where I just read the voltages. I can read this voltages, or this voltages. So there's always 2 configuration. You can read the counterflow resistance, which is longitudinal. Also, you can read the counterflow hole resistance as well, right? Both of them actually goes to 0 when there's a condensation happen. Yeah.
But there's other leads that connect these to
Yes.
make sure
Yeah. That's right. So I just right. So this 2 arrow is the same magnitude, which means actually conventionally we just connect them together, right? All right. So this is basically plot that how this counterflow resistance got changed with the temperature and magnetic field, right? This dark blue area is where that I have the 0 counterflow resistance. Therefore, I have condensations. And as you go to the higher temperature in all magnetic field, this turn into the dark red, which is basically finite resistance, several kilo. Sorry, the unit is missing. It's actually reach up to several tens of kilo, right? So we know that system undergoes from condensations from non-condensations. And more like the white colors, which is somewhere in the middle point, is kind of telling us there's kind of interesting phase boundary between this condensation and non-condensation state. Already you start to see that it's kind of strongly hinted. Maybe this type of the phase boundary quite resemble to the extern phase diagram I just started with, right? So not surprisingly, that's kind of the direction we are going there. But first of all, let me just kind of point it out that when I just look at these diagrams, at the fixed magnetic field with a different temperature, we start to see that different region of the magnetic field shows a different type of behavior. So here's the plots, right? The first of all, in the low magnetic field, that this transition from the non-condensations to condensation flows rather kind of slowly. And later I'm going to kind of discuss that experimentally. This behavior, in fact, can be well described by this RNS plot with the sum of the activation energies, right? However, as you go to move into the high magnetic field, this counterflow resistance actually drops rather rapidly and kind of turn into the zero very quickly, right? So especially this is kind of interesting curve. If I just call this is not the counterflow, simply this is my resistance I'm measuring, it looks like almost kind of superconducting like the transitions, right? Indeed, I think this limits that in a sense that we can just tie them together in this way. When you have the small magnetic field, that this distance between our magnetic external distance is kind of rather long. So this is more like close to the BEC type of the limits. As you go to the increase in the magnetic field, that magnetic length becomes smaller. Therefore, that the distance between the magnetic extern, if you just call, becomes smaller compared with the extern size, magnetic extern size, which is again separation between these two layers. Therefore, this is more like getting to the BCS type of the limits in a sense. So that's basically what I'm going to argue by just kind of looking at these details of this behavior. And claim is basically I'm seeing the BEC to the BCS of the crossover into this type of the phase diagram. Right. This is kind of what I just mentioned, that analogy between these extern condensations and the magnetic extern case is kind of matched. Once I just identified what is the length scale, size of extern is determined by this separation of this two quantum or bilayer. Distance between the magnetic extern is determined by the magnetic length. So in a sense, while these are fixed, while the distance can be changed by tuning the magnetic field at the given the electron densities, I should be able to just sweep through that then the phase diagram simply just changing the magnetic field in the system. And I suppose go through this BEC to the BCS crossover throughout this kind of system. So that's basically the idea. So let me first kind of argue that, going to the low magnetic field, how these things look like. As I said, when I just look at the low magnetic field, the change of this counterflow resistance as a function of temperature is rather slow, right? In fact, if you just kind of plot it out into this RNS plots, which is basically low scale of the RXX counterflow and one of the T, you start to see that there is kind of nice linear regimes that you can assign some sort of activating energies there, right? This activating energy actually just scales quite well with the magnetic field. That small magnetic field activation energy is low. As you increase magnetic field, the activation becomes the larger. It turns out that I can just plot it out that this data with a different type of the quantumized system with the different separations, more like that there is a universal relations we can follow through. Before that, you just kind of start to ruin this activating behavior. Just follow through the one of LB type of magnetic length type of behavior. Tells us that indeed the governing factor of this type of activation behavior is a deeply rooted Coulomb interactions between the electrons in partially filled Landau level. Mathematically, this type of the ground state, especially in BEC limit, can be rather nicely mapped into the XY systems. And then creating with the temperature, the ground state of XY system can be developed into the anisotropy SU2 by just creating the excitations in that kind of opposite layers. And in this type of the system, it has been discussed that the elementary excitations to create those kind of the non-condensation behavior is by just creating this so-called the metons and antimeton pair into the system. And meron and antimeron pairs, when you just create it, will require certain mass system energies, and that's basically more or less tied with this activation energy gap. So based on that previous research done into this quantum bilayer, we know that more or less follow through the very similar ideas of the creating those kind of meron and antimeron pairs. Now, what is the exciting part is basically the opposite side of the limit, which has never been explored before. And part of the reason that this can be explored now is basically, again, we can just feed it up with the relatively large densities and creating the large magnetic field, really getting into this BCS type of the limits, right? And in these limits, basically, as I said, that the counterflow resistance drops really rapidly to 0 as you just decrease the temperature, right? So almost look like superconductor and look like the 2D superconductor in a sense. While though this is not the kind of truly superconductor per se, because it is still insulator, or I think, well, the edge state can carry the current, so it is not the edge insulator, but it's a bulk insulator. So it becomes only superconducting when I just send the current in counterflow geometry. But nevertheless, we can just kind of, if this is a 2D superconductor, we can do the following things. 2D superconductor, suppose undergo the Kosalis-Dowless transitions, which means that in terms of this voltage and current characteristic, there is a particular relation we expect to see, that especially it shows some of this the power law behavior between the current and voltages. So what we did is we just measured the IV characteristic in the counterflow geometries and just plot it out in terms of the power law dependence. So here is a log scale and double log scale. What you see here is as you just in the higher temperature, basically it kind of shows a nice linear ohmic behavior. But as you go to the lower temperature, it becomes quickly that shows this kind of steep power law type of behavior, showing that the nonlinear IV power law type of IV behavior, and just kind of exponent try to extract this exponent of this nonlinear or power law IV behavior. One can extract this exponent, and that exponent, according to the Kosalis-Dowless transitions, contains the information about what is the transition temperature. So out of this, the fitting across all this curve that we are measuring this high in the BCS limits, we can extract it. What is this energy scale that related with Kosalis-Dowless transition temperature, right? It turns out this temperature scales, again, nicely scales with this D over LB, the magnetic length scale, and there is some sort of universal curve that one can expect to see in this the BCS type of the limits, right? Now, how do we explain those kind of behavior? This requires understanding of the what is a really ground states of the wave functions that we expect in so-called the BCS type of the transitions. Well, there actually quite of the competing ideas out there. So let me just kind of put up there that there are kind of a couple of the ground state proposals there. I don't know which one is kind of really the correct at this point, but at least we can point it out that those kind of scaling behaviors should explain that this nice the BKT transition temperatures as a function of D over LB. It seems like there's some sort of universal curve that I can write down in this way experimentally. So whatever theory, the ground state you can explain about this the BCS limits of the magnetic excitation should explain that this general behavior we see in the experimentally. So at this point, what I just kind of present here is indeed having this magnetic excitation systems and just having this the knob that we can tune around with both magnetic field and the temperature, we can explore this the ground state or the thermodynamic the phase diagram of this magnetic excitation for the first time. All right. In fact, this is just a kind of starting point, right? I just showed you that we can just create a magnetic excitation in the new totalical 1, the Landau level, which means that both of the half-field Landau level, right? But in a sense that there are many different Landau levels I can combine. I can create the magnetic excitation condensation with a very different type of Landau levels. In fact, each of the Landau level on the strong magnetic field, their spin and the valley structure is kind of they can be controlled, such that you can create the magnetic extons with a different type of valley configuration or spin configuration in general, right? So there are a lot of different type of phases I can just explore in this. The phase space we can explore by the changing of this gate voltages. I want to point out the one interesting state though. If across here, this is at the magnetic exton condensation nu total equal 1, but as pointed out, in fact, it is in some sense both the electron field Landau level, and I just try to make the analogy of the exon by converting electron to the hole by just particle-hole the conjugations, right? So in a sense, it is not really electron to the real hole, right? However, graphene, we have both the electrons and hole can be populated by just simply changing the gate. For example, across this line, where that the total filling fraction is always a 0, is a very interesting line, because in a sense, across this line, when the exciton condensation is happening, that's exciton really form the electrons in the electron Landau level and hole in the hole Landau level. So it's a real exciton, close to the real exciton. What is the advantage over there? Basically, along this line, there is no edge state, because if you project it into the electron and hole together, basically there is nothing, right, into the 2D layer. Therefore, there is no real quantum or edge state in there. So it's everything is basically carried by just a really bulk current, if there is, right? So indeed, we just kind of created some of these states, the electron hole Landau level, and kind of do the kind of following interesting experiments. So we just kind of stay to nu total equal 0, right, and just do the experiments. And you see that all this resistance, conductivity, actually drops down to 0. Basically, it's a true insulating states. All the drag hole, drag conductivities, the longitudinal transverse and drag, everything goes to 0, right? So it is a 0 conductivity state. It's kind of insulator. So, okay, so but it's not exciting in a sense. There are a bunch of the different type of insulating states. However, there's kind of one interesting experiment we can do. This is still superfluid state in a sense that it's a counterflow geometry. I can send this dissipationless current. So how do we do the experiments? You just kind of choose. So this is exciton insulator, counterflow geometry, or the other way, that equivalent way is you're sending the current in one of the directions and basically measure the resistance in other directions, right? Or they measure the current in another direction. So this is a direct current measurement, the same kind of type of measurement. And if you just do that, you find out whenever I send the current here, I should send the current in opposite direction. There is automatic current flow in the opposite direction. Or if I just connect them into counterflow geometry, there basically you get, again, 0 resistance state. So it's two insulators, but if you just put them together, it becomes kind of perfect conductors again, right? So that's basically kind of what we can realize into this particular cases is the exciton insulators, but truly exciton insulators without edge states, which actually also can carry the current. So compare with this kind of previous, and they also shows kind of very similar phase diagram as I mentioned, with the magnetic field and the temperature, we can control this phase of the exciton condensations, right? So summing up onto the sectors, that what I can say that is, depends on which Landau level you just kind of decouple together across the quantum or bilayer. You can get this exciton condensations, but certain cases exciton condensations happen at the bulk superfluid state with the superconducting edge states, more like the analogous to the topological the exciton insulator, or that you can turn into the real exciton insulators if you just couple the real electron and hole Landau levels together. In both of the cases, that you just get this superfluid, the conduction happens by the counterflow geometries, right? So going forward, where we are going onto this one. Now, I just kind of show that we can couple any Landau level, partially filled Landau level, complementary filled Landau level, we can couple to make this magnetic extons, and they can condensate as a composite boson. But one thing that I didn't tell you yet is, well, if we just kind of have the really clean sample and strong enough magnetic field and reasonably low temperature, electron-electron correlation within the layer cannot be ignored. And of course, we know that there's beautiful series of the fractional quantum Hall effect can set in graphene in partially filled Landau level, right? So interesting idea is, can we actually couple those kind of fractional quantum of states together? Well, the answer is yes, indeed. So this is one of the kind of best sample, and then high enough magnetic field. And then we start to see that within this filling fraction, note that this is 0 and 1 and 0 and 1, right? So this is the previous action condensation we are discussing. I just note that I'm just kind of showing the drag x-axis is as my tool. So drag x-axis becomes 0, which is white color. And that's where that I see that action condensation is happening there. But other than this new total equal 1, you start to see that system shows a bunch of this kind of rather intriguing, the phases there, right? So there are a bunch of these lines out there showing that there's other type of this condensation type of the phenomena appears. It turns out this across this line, for example, this kind of particular line, two lines that I show you, is a line through that where that extant condensation is, well, I shouldn't say extant condensation, binding between the two different quasi-particle in two layers to make some sort of the condensation states. For example, across this line, very close here, that where this, I start with a 2/3, but with 0, or that it's a 0 in the electron lambda level, becomes a hole in this hole quasi-particle is across here. So this hole in the bottom layer coupled with the 2/3 of the quasi-particle into the top layer, and they form this kind of still condensation state there. And then very close to here, that's basically 2/5 and 2/5, that both of the layer, 2/5 of the quasi-particles, and they can still form this kind of condensation states, right? So there's quite of this, the states you can make. An interesting part is across here, the continuous condensation is happening. And when you measure the parameters across this line, we start to see that there is some of the semi-quantization is happening, indeed indicating this is kind of described the condensations. I don't want to go to that kind of too much of the detail onto this story for now, but this diagram tends to show us now with this high quality of the quantum mobile layers, and especially each of the layers start kind of form the fractions. And since we just can put these two layers very close by, but without tunneling, we start can make the coupling between this one quasi-particle to another quasi-particle is another layer, and not necessarily this quasi-particle is electronic holes, but it can be anyons of this fractional quantum state. What is a quantum statistics, or what is a kind of proper way of quantum description of this system is something that kind of quite interesting and exciting thing to explore, and this kind of just happened for now, right? So that's kind of one story I want to kind of share with you. Questions? All right, I have 7 minutes. 7 minutes too short to go over. Next topics.
Okay, we have 17 minutes.
17 minutes, okay, good, yeah. But then let me just kind of talk about the other topic, which actually also discussed kind of multiple times, so I can skip most of the stories, and I will jump into the some of the important kind of development later part. So the second story that I want to tell you is about the this twisted the layers forming the two-dimensional system, and particularly this system that I want to discuss about is a twisted double bilayer. This two layer of the bilayer graphene on the top of the bilayer graphene. That's basically the story I want to tell you. Again, the main experiment was done by the Xiaomeng Liu and Jiu Hao, the previous the guys who did the mostly previous experiment. Theory support is done by the Ashbins and Zhongyan Li and the Islam Club. All right. So graphene has been studied many years, as I said, right? There are many things we discuss, part of things we discuss. But one thing that has not been discussed until kind of 2 years ago is something like the superconductivity and magnetism, intrinsic superconductivity and intrinsic magnetism. There's a reason that quickly that we can come up with this. In a sense, Liang Pu's talk in the previous sections already mentioned that, right? In graphene, near the neutral point where the most of the physics we are studying, density of state is vanishing. So a lot of this superconducting magnetism where that you want to have the larger density of state is not preferable in the graphene. So that's kind of has been the issues. Of course, this story got changes quite recently, especially when just the twist bilayer is available. And throughout the twist bilayer, you start to create this the very flat band in some specific angle with well control. Again, Oscar's talks in this morning already explained this one. You can create a very flat band with a large density of state, which actually can promote this very correlated effects, such as superconductivity, multi-insulator first, and then doped multi-insulator to turn into superconductivity. Magnetism is reported in certain kind of feeling in the specific conditions. So I don't want to kind of go over the details, but this becomes quite interesting stories already discussed, right? So I would say that why we are interested in kind of the bilayer. That claim that I want to make is basically in the bilayer, the bilayer on top of the bilayer, say double bilayer system. There's a possibility that we can create yet kind of different type of the correlated states. I would say that tentatively it is ferromagnetic superconductors, right? It's a little bit kind of the bold claim. I would say it's a still bold claim. In the end of the day, we'll see that whether each of the statements we have to carefully re-examine, is this really ferromagnetic? Is this really superconductivity? But for now, let's kind of start with that bold claim. Well, in a sense, this ferromagnetic superconductivity sounds like already oxymoron, right? Because as I kind of said in the first lectures, well, usually, you know, the ferromagnetism and superconductivity compete each other, especially if the superconductivity is based on S-wave type of the superconductivity, where that you want to have this singlet of the electron couplings to form the Cooper pairs. However, in fact, this ferromagnetic superconductor is actually do exist, and there are a few examples out there. For example, especially when you just kind of breeze through that the heavy fermion system, especially uranium compounds. The first report of the uranium-germanium-2, there has been report of the ferromagnetic superconductivities where the magnetism actually sets in around the 40 Kelvin of Curie temperature. Clearly, superconductivity appears something like the below that, I think it was 0.4 Kelvin or something like this, right? So that's kind of the first example. And this example shows that the kind of good starting of this ferromagnetic superconductors. However, this system is only stabilized, they appears only under the magnetic field. But soon, some of the other uranium compounds actually shows that indeed there is a kind of well-established field of the ferromagnetic superconductors. Again, the series of the uranium compounds, and most of them, and especially the most recent uranium, cobalt, germanium cases, that they can show both the superconductivity and magnetism even in the room pressure. So that is quite kind of interesting. One of the signature of this ferromagnetic superconductor is their HEC2 line is quite kind of unique, especially when the magnetic field is on the EG-axis of the magnetisms onto these crystals. Usually, this HEC2 line shows some of this non-monotonic behavior, and that is one of the signature. Or some cases, there's even just a re-entrant behavior of these HEC2 lines. I think that's kind of one of the evidence that often that intrigued people about these ferromagnetic superconductors. Although there is a strongly hinted, because as I said, S-wave superconductor is a rather strongly the prefer of the spin singlet type of the Cooper pair, which can be easily destroyed under the magnetisms or strong internal magnetic field in the magnets. Therefore, it implies at least that there is a preference of the P-wave superconductors onto this type of system. There has been no yet kind of direct proof that the ferromagnetic superconductor really support the P-wave superconductors yet. And everybody got excited about the P-wave superconductors because that's, especially nowadays, that's a way, the doorway you can realize topological superconductors, which you can just use some of this more topologically protected quantum computations and so on, right? In fact, nature provides us one really important system that everybody agrees on now. It is coming from the P wave of the pairing, and that's basically superfluid helium-3 phase A, right? In this particular case, that the superfluid helium-3 atoms, the couples to form the Cooper pairs, as a fermion, they form the Cooper pairs, but they prefer to form the P wave, the pairing, Therefore, that the spin sectors turn into this spin triplet states. Therefore, when you apply the magnetic field in this type of the system, that you get this kind of two different type of the phases, right? So either the ferromagnetic phase, spin-up phase, is aligned with the magnetic field, anti-aligned with the magnetic field, and both of them actually split the Fermi surface with the different sizes, and hence that actually change the density of state at the Fermi surface, which were actually 10 minutes, okay, yeah. They turn into the different type of this transition temperatures. So clearly, when you apply the magnetic field in the superfluid helium-3 and just measure their transition temperature, there is the separation of the transition temperature for the major spin species and minor spin species, and the separation actually tuned by the Zeeman splitting of these energies. And that's kind of one of the strong evidence of this type of the system. All right, since I don't want to kind of go over too much of details, so let me skip the more things. Second part of is whether multi-insulator need to be always antiferromagnetic, because I want to kind of discuss that there is insulating state appears, and that's a spin polarized, and that will also to support this the superconductivity when it's stopped. It turns out multi-insulators typically is antiferromagnetic when this orbits the responsible for the multi-insulator is well localized because of the short rangeness of the exchange interactions. However, if the especially orbits that responsible for the multi-insulator is rather extended 1 year orbits, as we just discussed, it's not necessarily that antiferromagnetic interaction is basically dominant. In fact, there are few examples that people discovered that ferromagnetism in the multi-insulator in some of the more complicated oxide system where the super-exchange interactions actually prefer the ferromagnetic interactions between these spin diagrams. So in principle, that depends on how you realize the strongly correlated system and details of the wave functions. That still magnetism can be appears in the certain system with the multi-insulators. Now, how about this twisted bilayer graphene? It turns out twisted bilayer graphene, already Pavlov's group actually demonstrated, once you apply the magnetic field, you just kill this multi-insulator with the magnetic field. Part of the reason they believed is the multi-insulator is spin unpolarized at least, and then when you apply the magnetic field, simply Zeeman splitting will just close mouth gap, and therefore you just kill the multi-insulators by just applying simply magnetic field, right? So at least we know that in this twisted the bilayer graphene, it is not the ferromagnetic system or spin polarized system. Now we decide to move on. Yes, yeah. Correct. That's right. Yeah, yeah, correct. Is it right? I think I don't remember again. I think it should, right? Because all this state is basically spin and valley is polarized. Correct. Yes, right. Now, twisted double bilayer. There is one. The initial reason that we started out twisted double bilayer is because there is a certain the knob that we can tune around. Oscar already mentioned it, so I can just kind of skip it briefly. So in the twisted monolayer graphene cases, this mouth gaps and that all this band structure is basically fixed by just the angle. And once you fix the angle, basically state is basically the band structure is fixed. However, in the bilayer graphene, again, that angle will control this hybridization, but on the top of that, applying the electric field can also tune your band structures. Especially, we know that even just kind of single bilayer graphene, applying the electric field open up the gap by just breaking the symmetries, inversion symmetries. In the same very similar way, applying the displacement field, electric field in the vertical directions, we can tune the band structures quite a bit, which means that in a sense, we don't necessarily need the precise control of the angle. If you have this kind of different angle, then just kind of claim the magic angle. You can always tune your band structures by this electric field to tune the angle into the magic angle. Now, of course, this is kind of simple ideas that there's some band calculations there, and that there's regions of this the insulating state and appears with the stabilized of the electric field. But quickly getting to the data, basically this is that two gate voltages control the electric field and the density into the system. So along this line, basically we control the electric field. Along this line, we just kind of control the fielding. So we have the discharging actually point which actually open up the gap. So this is kind of single particle effect, we know that. And this is a full filling states, also kind of open up the gap. Not surprisingly, again, that the very similar stories. But what is interesting part is this half filling states. Originally, there is no gap. But once you just kind of increase the displacement field, you start to see that there is a gap opens up. So again, the idea that we can tune these band structures to open up the gap actually seems to work it out quite well. So detail of the temperature scans, we can see that the gap size of the gaps and all the band mass. But let me skip this one. But let's discuss about field effect, the magnetic field effect. So one way we know that what is this nature of the spin configuration is, again, as I just kind of mentioned, applying the magnetic field, especially applying the in-plane magnetic field only coupled with the spins, and see how the gap got changes, will tells us what is the spin configuration of the system. And what we did here is just basically choose one of the line as throwing up the displacement field such that this half field gap opens up, right? And applying the in-plane magnetic field and see how the gap changes. Quite surprisingly, in this system, as you increase the magnetic field, both the half field and full field, half field and quarter field, the gap actually increases with the in-plane magnetic field, indicating that, in fact, this is a spin polarized states. Indeed, the increase is more like to follow the Zeeman energies, and strongly kind of indicating that the gap that we have here is all kinds of spin polarized gap, right? Which means that in some sense, the ground state is preferred to filled up with the kind of ferromagnetic spin polarized states. So that's kind of first discovery. Second discovery is basically when you apply the density away from the ferromagnetic insulating states, and then changing the temperatures and measure the resistance. And as you see here, the resistance actually drops down to 0 and shows like the superconducting like the states. And indeed, IV measurement shows the Kosalis-Staulis transition type of the behavior, where we can also extract this transition, BKT transition temperatures out of this type of the nonlinear IV measurements. And using this one, in fact, let me skip this one, and map it out, how the transition temperatures change with the magnetic field. And it turns out these transition temperatures actually start to increase with the increasing magnetic field in the beginning and eventually kind of decreases down, right? And this linear increase is very analogous to the helium-3 system we actually, I just kind of briefly mentioned before. So it seems like it's indicating, indeed, it's a spin polarized ground state, and dope it, turn into this is more like the ferromagnetic superconducting state with some sort of the equal spin pairing of the Cooper pairs as kind of naive stories goes down, right? However, this is something that we have to be a little bit careful, and the exams a little bit carefully, because that's kind of some story I want to kind of tell you in the next 2 minutes. Liang actually shows again the data from the other TMDs. For example, the tungsten diselenide, the twisted layer. If you just can put the sum of the angle, it's also Corey's groups shows very similar things, and cool it down. You often get this kind of zero, like this, the zero resistance state in the finite temperatures, with very similar to this the nonlinear IV characteristic, which mimic the superconducting transition temperatures, right? Particular sample that we had, the best sample here, that you see that zero resistance appears in this, I thought kind of this is about 2 degrees. And if I just kind of follow where is my transition temperature, now that's something like this kind of A Kelvin or something like this. So it turns out many of these twisted layers, when you just combine together with make this resistance measurement, you often get kind of zero resistance state and look like the superconducting like the states. But the question here is this really superconducting states? And that is a really hard question. Because typically when we prove that something is a superconductor, and of course we want to have the zero resistance state, right? But that's often not enough, right? What do we need? We need other thermodynamic measurements, something like the Meissner effect. However, by the way, in two-dimensional system, Meissner effect is very difficult to measure. And it's almost non-measurable, right? Because your screen current is out there in the edges, right? Any small magnetic field almost immediately jump into the sample by definition. So just looking at the zero resistance state, I claim the superconductivity is a little bit weak claim. And it's actually even more, right? I mean, let me show you that out of the 1 year of the kind of hard efforts, we are just trying to make the sense out of it. Some of the samples indeed shows like this kind of very low resistance state, the so-called superconducting state I showed you here, right? But if you just choose different angle, different ranges, there are often that maybe this sample is more inhomogeneous, like the phase transition. Some of the sample is just really slow, but even hit the zero resistance like this. At this point, I would say that just showing the zero resistance state, not sure whether I can call this is a superconductor, right? So what do we need? Well, twisted bilayer is a good example that what we really need to show that kind of what is a kind of sense, the evidence of superconductivity. At least you need additional evidence that showing that whether there is a phase equivalence type of the measurement is possible. Luckily, in the twisted bilayer cases, there are enough, the right amount of disorders that create the inhomogeneous superconducting coupling in the sample, such that when you just kind of hit the right ranges, you start to see the Fraunhofer pattern type of the patterns coming from the accidental intrinsic Josephson junctions. None of the samples that we've been seeing that so far. We haven't seen those kind of Fraunhofer patterns that has been seen in the twisted bilayer graphene. So I would say that at this point, while that this spin polarized ground state is a rather solid evidences, but showing this zero resistance, whether I can just take that as that evidence of superconductor, there is some of the inches short of the feeling that I have. Yes, indeed, IV characteristic look like the BKT, like the transition temperature. And when I just draw the phase diagram, it makes sense. But is it really enough to call the superconductivity? That's kind of way to see. I will just stop it there. And there's enough reason to believe that because a realistic sample, there's always disorders. Yeah.